we're now going to discuss a specific class of classifiers called nearest neighbor classifiers. They're important for several reasons. One of them is that they're actually quite simple and widely used. And to be honest, if you ever have a machine learning problem or you have to do supervised learning, you should always try nearest neighbors, just because if it works, there's no need to work further. The goal here is to introduce them and actually argue that under some conditions, they're actually the optimal thing to do, perhaps surprisingly. So what are nearest neighbor classifiers? We're going to go back to the notation I had used in the first few lectures, where I don't use capital letters to denote my feature vectors, because even though they're random variables, I don't want to carry the burden of capital letters everywhere. So this is the notation for my data set, lowercase x for my feature vectors, lowercase y for my labels. And we're going to define the one nearest neighbor, or to make things shorter, the nearest neighbor classifier, as follows. The output of your nearest neighbor classifier KNN applied to a feature vector x that you might not have seen before is equal to the label of the nearest neighbor of x, where the nearest neighbor of x is simply defined as the vector in your data set xi that is the closest to the point x that you're trying to evaluate. I want to highlight several things. If the point x at which you are trying to evaluate the label is indeed a point in your data set, it means that x is of the form xj. In this case, the nearest neighbor of xj is xj itself, according to my definition, in which case you return the label that you have in your data set. Keep that in the back of your head. We'll come back to that observation a little bit later. Now, it's possible to evaluate a little more precisely what the risk of the nearest neighbor classifier looks like and how it behaves. To start with, let me introduce a notation that is very specific here. Remember that when we're talking about the risk, there are two components that make it a random quantity. One is the fact that x, the feature vectors at which you might want to evaluate the true risk, is a random variable. But two, the label could also be random. So what I can do is I can also evaluate the risk conditioned on x and conditioned on what the nearest neighbor value of x is. And this quantity I'm going to define as RNN for x and x nearest neighbor of x. What is implicit behind that assumption is that I'm giving you a fixed sample realization of the new unseen sample, and XNN of x is fixed because I've given you a specific data set. To compute the true risk, we will have to average with respect to the distribution we use to generate x and the distribution we use to generate the data set. So when I write R with two arguments, it's actually something that only depends on the randomness introduced by the label. And it turns out that we can write that quantity rather explicitly in terms of the quantities eta k, the probability of y given x. And specifically, what I want to show with you is that it takes the form the sum over k, eta k evaluated at the nearest neighbor of x times 1 minus eta k of x. So let's try to establish that fact together. And the way we're going to do it is we're going to start from the definition of this risk condition on the value of x and the nearest neighbor of x. So that should also clarify what that quantity here is exactly. So RNN of x, x nearest neighbor of x. Okay, so one thing I really want you to remember is when I write x nearest neighbor of x, this is a point or a data point or a feature vector in the data set D. Whereas this one could be anything, any feature vector in the space of feature vectors x. So if you followed my introduction, what this quantity is, it is the probability that the label that you assign to the nearest value x is not equal to y, the label of the point x. Okay, and this is condition on x, nearest neighbor of x. Okay, so understand here we're conditioning on this value. Is our value as fixed. And the probability is over the distribution that generates the nearest neighbor and the distribution, the nearest neighbor label, sorry, and the distribution that generates the label of the point x. So if you explicit what this quantity is, it is the sum over all possible values k taken by the label y, probability of y equal to k, given x and given x nearest neighbor of x, times the probability that the nearest neighbor of x here is not equal to y, given y is equal to k, x, and x nearest neighbor of x. So let's decipher that expression together. So what I'm applying here is I'm applying the law of total probability, or LTP for short, expanding it on all the possible values that the label y can take. Now, what I'm claiming here is that several simplifications are possible because of the specific way we assume our model generates feature vectors and the way labels are associated to feature vectors. The first thing I'm claiming is that this quantity here, even though I'm conditioning on x and the nearest neighbor of x, according to my model, once you have a feature vector, its label is generated according to py given x, independently of the other points. And so that quantity here is nothing but, so I should be careful, I write equal by definition, but it's equal more because of my model. It's equal to p of y equal k given x. But that's exactly what we call, by definition, eta k of x. Now, if you look at the term on the right-hand side here, this is the probability that the label of the nearest neighbor of x is not equal to y, given that y is equal to k, and given that you know x and the nearest neighbor of x. So what I'm claiming is that this can be simplified too, because this is the probability of the label of the nearest neighbor of x, y and n of x, not equal to k, because I'm conditioning on y equal k, given that y equal k, x and x nearest neighbor. But again, if you know the nearest neighbor of x, you know that the labels, according to the model that generates our labels and our feature vectors, tells you that once you know the point, you're generating the label conditioned on that point, but independently of everything else. So that takes that simple expression. And this is nothing but 1 minus eta k of x nearest neighbor of x. And so if you put everything together, you get that expression where you will find it's the sum over k, eta k of x times 1 minus eta k of x nearest neighbor of x. Now, if you look at what I've done and look at it in the eyes, there was really no reason for me to expand using the law of total probability depending on the label y. I could have done the exact same calculation by starting the law of total probability, expanding on the values of the label of the nearest neighbor of x. And so if you redo that calculation, you should be able to convince you that what I would get is exactly the same result simply by changing the roles of x and its nearest neighbor. So that has to be equal to the sum over k, eta k of x nearest neighbor of x, times 1 minus eta k of x. And if I have not made any mistake here, it should be indeed what I was set out to prove, and I believe that it is. Okay? So this is not exactly the risk of the nearest neighbor classifier, because what I'm missing here is I'm missing an average on how I generate x and how I generate the nearest neighbor of x. I've only computed the conditional risk given the feature vectors x and its nearest neighbor in the data set. So we'll get to that in a second. The question that we're going to try to answer based on this calculation is how well does the average risk, RNN, which is R of the nearest neighbor classifier, compare to the base risk for large n? And there's a very surprising result here that relies on us establishing two lemmas. There's one technical lemma that I included in the lecture notes that we're not going to prove together. The reason I'm not going to prove it in class together is because it's a bit technical. It relies more on probability theory than anything else. But I want you to understand that this is the kind of questions that people who do theoretical learning theory worry a lot about. How can we describe the problem of learning in an abstract way so that we capture the most situations possible? And the first thing that they prove in the context of analyzing the risk of the nearest neighbor classifier is a result of that form. They say, let's assume that we generate an unseen feature vector x and a data set consisting of point xi from I equal 1 to n, id according to px. These are the standard assumptions that we made in the previous lecture, but then they qualify it saying that it has to be in a separable metric space X. So a separable metric space X is a bit of a mouthful here, and it's a bit of a misnomer because it really means that you operate in a space of feature vectors where you can always find a dense, capable dense subset in that feature vector. What it really means is it means that no matter, how you sample, you will always be able to sample a point close to any other sample. That's really why that assumption is there. It's a mathematical formulation of something that I believe is somewhat intuitive. And what they prove then is that the nearest neighbor of X converges to X with probability 1 as you increase the size of the dataset to infinity, which is something that is maybe very intuitive to us if you had not tried to formalize it exactly. The idea is that Px represents how you generate your samples. The more samples you generate, you should be able to approach any point that you might want to evaluate. But it turns out that mathematically, if you want to be more precise, you have to be a bit more specific as to the kind of spaces in which your feature vectors lie, which is here a separable metric space. Again, the full proof is in the lecture notes. I don't expect you to fully reproduce such details. It's more for reference to understand what learning theorists might care about.